Hello, class. Welcome back. This is lecture 15. Today we're talking about Legendre equations. Very fancy type of equations named after a mathematician. And we're going to solve these. Okay, so next we'll solve class of equations. So we're not just going to solve one little baby equation. We're going to solve a whole bunch all at once, a class of equations called what I just said, Legendre equations, and they look like this. I should put in parentheses of order m. So what's different about these is there's a whole bunch of them, one for each value of m. But what we're going to do is we're going to keep this m as arbitrary, so that we can solve them all at once. So if I just plug in various m values, I get different differential equations. So if I plug in like 0, I get this one. I guess that would just be 0. If I plugged in 1, then everything would be the same, except at the end, this would be a 1 times 2y equals 0, but the rest would be the same. If I plugged in 2, I'll just do one more. This would all be the same, but this would be 2 times 3, so it would be a 6y. This would be a 2y, and so on. So you get different differential equations depending on m, and we can solve these using a power series technique. So just another application of what we learned yesterday. But what's going to be interesting is, just like in one of the examples I did yesterday, the solution, what's going to happen is, I'll just give you a preview. So we'll get something like C0 times one function plus C1 times some other function, some other series, I mean, where for even m values, so like if I plugged in 2, 4, 6, 8, and so on, I forget which, we'll see at the end, one of y1 or y2 will reduce to a polynomial instead of a power series. So it'll just stop. It'll be like something x plus something x squared plus something x cubed, and it'll just stop. That's for even m. And then for odd m, it'll be the other one. It does the same thing. So we'll see that at the end. And these polynomials that you get have very special properties. Okay, so let's get started in solving this class of equations using a power series. So what we're going to do is we're going to let y equal a arbitrary power series where we don't yet know these coefficients. And then we're going to take derivatives, plug them in. That's the same as last time. Simplify as much as possible and see what happens. Okay, so what's y prime going to be? So I bring the power down, subtract 1 from the power, and y double prime will be starting at 2 now, because the first two are 0, n times n minus 1, x to the n minus 2. Oops, I'll often forget to write the constant, but that's the whole point, is to find those things. Cn x to the n minus 2. Okay, so we got these three things, plug them in, and let's see what happens. So the first term has a 1 minus x squared coefficient in front of it, and that's in front of the y double prime. So now I'm going to plug in my y double prime. So this thing here, And then the next one had a coefficient of minus 2x. And that's where the y prime will go. And the last one is the m stuff, m times m plus 1. And that's where y goes. And I want this to all add up to 0. So again, the point of solving using power series is to set something like this up and then determine the c's, where because we're doing second degree differential equations, it'll typically be that there are 2 c values that remain arbitrary, and the rest are written in terms of those 2. So that shows up once we simplify. Okay, so how are we going to simplify? We are going to distribute this sum in here. So I'm still going to get the same exact sum when I distribute it to the 1. But then when I distribute it to the minus x squared, I'm going to get a minus, and I'm going to bring that x squared in. And then I'm going to combine x squared with x to the n minus 2 just to get x to the n, because it's x to the n minus 2 plus another 2 x's, cancels that minus 2 out, and there you go. Then I'll pull this in here. So that'll just be minus, whoops, I said I will take it in there, and I will. So minus 2 n cn, and that x now becomes x to the n. And then I will bring these both in here, and I'm just going to leave them separated for now. That'll be the easiest way to handle it. Okay, so now we're here. So remember that in order to combine these sums, they need to have the same power of x and start at the same number. So that's actually not so bad to do. So for example, because if I plug in the 0 term, I get 0, I can just combine that and start at 0. So I'm just going to go ahead and do that. This one is already good, so I'll just leave it there. So now if I want this one to start at 0, I can do the same trick, because when I plug in 0 and 1, this is 0. If I plug in 0, making the whole thing 0. If I plug in 1, this is 0, making the whole thing 0. So those terms don't actually add anything, so I could just sneak them in as well. I don't know if I left enough room. I did. So I can do that. Now this guy, the first one, I need to add 2 to all the n's to make that be a x to the n. And when I do that, I have to subtract 2 from the indice. So that gets me to 0 exactly as I want anyway. And then all these n's turn into n plus 2's. And that plus 2 and that minus 2 cancel. Good. So now we're in a situation where we can combine it into one big old sum. So n plus 2, n plus 1, cn plus 2 minus n times n minus 1 times cn minus 2n cn plus m times n plus 1. All of that times x to the n equals 0. So now I know that I need my coefficients to equal 0, which means that now I can just change, basically get, the next step is just writing the same thing down without that sum. And now there's a lot of stuff you could do, but this is where going through it ahead of time pays off because there's so many different things you could do. Oh, there should be a CN here as well. So what we are going to do is we are going to put all the CN terms together. So this CN plus 2 term is just going to be well and good sitting alone. But then all the CN terms I'm going to stick together here. 0 still. So I have a minus n squared plus an n minus a 2n plus a m squared plus m cn. And we're going to have to bring in our old pal algebra and do a sneaky little trick here. So, oops. So let me write this in a very specific way. I'm going to write it as m squared plus m minus n squared. These become a minus n. And now this thing, I'm going to rewrite it by doing a little trick. I'm going to do plus mn minus mn. And then if I do that, which I can because that's just adding 0, then I will be able to factor this, and you could check this on your own. If you multiply this back out, it will become that stuff. But this is just a much nicer form. So we're going to keep it like that. And now what's the next goal is to write the future term in terms of the previous term. So we're almost to that point. You just have to subtract this piece over and divide by this piece. And that gives us our relationship between the future terms and the previous terms. And then we just start plugging in values of n and see if we can see a pattern. So this we need to be true for n equals 0 and up. I should have written that earlier, but that's because the sum started at 0. Okay, so now we'll plug in 0 for n. And what do we get here? What does that tell us? That tells us that C2, 0 plus 2, equals negative m times m plus 1 over 2 times 1, C0. Okay, maybe I'll do this side by side because it's going to turn out to be an even and odd pattern. So if I do 1, so I plug 1 into this relationship there, then I get C3 equals negative m minus 1, m plus 2. And then on the bottom, it's 1 plus 2 is 3. 1 plus 1 is 2. So 3 times 2. And then n is 1, so this is C1. Okay, so now let's do n equals 2. So 2 plus 2 is 4, so that's why this is telling me C4. Negative m minus 2 m plus 3. And this is 3. It's 2 plus 1. Sorry, no, 2 plus 2 is 4. Oops. Be very careful. And then 2 plus 1 is 3. C2, but then we already know C2 in terms of C0. So putting this there gets us the following. So C2 becomes negative, so we're going to see that the negatives will cancel, but then we'll start to see the pattern form. C0. So what's on the bottom there? That's a 4 factorial. And on top, the negatives cancel, and I'm going to write this in a specific order so that the pattern starts to appear. M minus 2 is I'm going to put first. I'm going to put them in order, and then M is after that. And then what's next would be N plus 1 and N plus 3. C0. So before I do N equals 3, let's just do N equals 4 while we're on the even side so we can see the pattern. And establish what's going on. So I think one more will show us the pattern. Okay, so C6 should be still using that same formula. So what's happening is when I plug in N equals 4, I'm getting a new M minus that number. And then I'm getting an M plus the next number, 5. So there's this, and then on the bottom would be 5 and 4. And then C4. So let's see if we could see what's going on. So each even number that I plug in, so I plugged in 2, that gave me an M minus 2 and M plus 3. Then I plugged in 4, that gave me a 4 and a 5. So I had a 2 and a 3, then I got a 4 and a 5. When I plug in the next one, you might want to guess 2, 3, 4, 5. Next would be a 6 and a 7. It would be an M minus 6 and M plus 7 on the top. And so I'm just adding in the previous, all the previous minuses and pluses, and then 2 more. And on the bottom, I just get a bigger factorial. Actually, that 5 doesn't look right. It should be a 6 times 5, right? Yeah, 4 plus 2. Yeah, good thing I caught it early. That should be a 6 times 5. Now we are good. Okay, so then when I plug in the C4 term, I plug in the previous term there and rearrange, you might start to see the pattern. So I have this 4 factorial, which is going to combine with that 6 times 5 to make a 6 factorial. And then I have these other terms here. And all I'm doing is going out one more odd number and backwards one more even number in terms of subtracting and adding. So now I go to the, you can think about it as like left and right. I go down to 4, to 2, now there's a minus there, to M plus 0, and then I do M plus odd numbers up to 5. M plus 1, M plus 3, M plus 5. So the true test is if I can predict the next one. So this will be C0. So without actually plugging everything in it. So if I do N equals 8, can I see the next one based on this pattern? Or sorry, 6 is the next one. So that would tell me C8. And this pattern, I think I got it now. The bottom is just that number factorial. So it's going to be 8 factorial, just like this was 6 factorial for C6. And then I'm going to go out to M minus 6 in terms of even numbers. And it's going to have the previous ones as well. And then I'm going to go M plus odd numbers all the way up to the next one. So M plus 3, is 5, m plus 7, C0. And now this one will not be negative because that negative will cancel. So that is my even numbers. That's like the pattern. The odd numbers will have a very similar pattern. Okay, so that was 1. So the next odd number would be 3. N equals 3. So that's going to tell me C3 plus 2 is 5. And I'm using the same formula. So negative, of course, I can't remember it very well, m minus 3 and m plus 4 divided by, what's 3 plus 2, 5, times 3 plus 1 is 4, C previous one, and then I replace C3 with all this stuff, and we'll see a very similar pattern once I rewrite it in the right order. So this will be negative m minus 1, m plus 2, 3 times 2, C1. Do the same sort of ordering. So I'll write them. So the negatives will cancel again, and I'll write that biggest minus to the left, m minus 3, m minus 1, and then go in order of pluses to the right. And the bottom is 5 factorial. So I think I can guess C7 now by establishing the same pattern. Oh, this is now times C1. So it's going to be a 7 factorial on the bottom, and I'm going to go out to minus 5. And I'm going to go out to plus 6. Oh, what happened to my pen? And plus 6. C1. And now there will be a negative on this one. So the negatives alternate because of the negative in the first, in the actual formula up there. Okay, so this is the pattern I've got going. And now we want to put it back together to actually write down the solution of the differential equation. So let's do that. Y equals, so remember the whole point is we have this power series and we're trying to figure out the C's, and the point is that the rest of these are in terms of the first two C's. So this will be C0 plus C1x plus, and now we've established what C2 is. So C2 was negative m times m plus 1 over 2 factorial times C0. So now that's it. That's what C2 has become. And then C3 was negative m minus 1, m plus 2 over 3 factorial C1 x cubed. Got to pause real quick 1 second here. Okay, so then that's that. And I'm not going to write the rest that I wrote because I wrote them up above until I reorganize to make it look nicer. So we want to put all the C0 terms together. And so notice the C0 terms all go with even powers of x. So x to the 0, x squared, x to the 4th, x to the 6th, and so on. So I'm going to put those all and then factor out C0. So if I factor out C0 from C0, I just get 1. And then I factor out from the x squared term, I just get this. And then now I'll write the fourth term because I didn't write it earlier. So but we did figure it out. So the x to the fourth term starts at 2 and then includes the previous ones and then goes to the next odd number, which would be 3. And it'd be 4 factorial on the bottom. So just as a test, you should try to write the next one without looking. I'll do it here. So the next one would be -4, -2, -0, +1, +3, +5, and then 6 factorial, x to the 6th, plus so on. So that is all, that's a whole power series on its own, and it's all being multiplied by C0. So I'm going to name that whole thing y1 of x, just so I can refer to it later. But then I'm going to also group up the odd terms. So those all go with C1s. So this is, whoops, in my pen. Give it a second. I'm sure it'll start working. Okay, I have to pause while I fix it. Be right back. Okay, so I fixed the pen. All right, so the C1 terms are the odd powers of x. So take out C1 from x, you just get x. Take it out from this thing, and you get this stuff, x cubed. So what's x to the 5th going to be? Oh, I just realized a mistake. So this, on the green stuff here, this is negative, positive. So this one should be a negative. They flip back and forth on the pattern. Same thing happens here in the blue stuff, the odd powers. So the next one you are going to make be positive, and it's going to go down 1 odd term and up 1 even term. Then it'll be that power factorial, so x to the 5th plus so on forever. So that thing I will call y2 of x. So we're basically done, sort of. So the solution to this differential equation, rewrite it here, is, I don't want to rewrite it all again, but it's this function C0 times that first power series, which I'm just calling y1 of x, plus C1 times the second power series, which I'm writing as y2 of x because I don't want to try to write it as just a thing like that. It's just a bit too cumbersome to try to make it look like one nice little thing. Because instead what I want to do is I want to think about what happens now for specific values of m. So that's the next thing to check out. Okay, so now consider different values of m. So for example, when I plug in 0, I get the differential equation 1 minus x squared y double prime minus 2xy prime plus 0 equals 0. So then what solves this? Well, the solution is this big old thing with 0 plugged in for m. But notice what happens when I plug in 0 for m to this green part. So what happens if I plug in 0? Well, this is 0, m is 0, so 0 times 0 is, this is all 0. There's another m here, so that's 0. That m is in every single term. So what happens is those are all just 0, and this just becomes C0 times 1 is the only thing left, equals C0. So the solution for m equals 0 is really just y equals C1 plus C2 y2 of x, where I do have to actually plug in 0 here, and these don't go away. Or now y2 of x has m equals 0 plugged in. So you could go ahead and plug those in. But what I want to focus on is this cancellation thing that happens and the answers you get when you plug in values of m for the parts that disappear. So that's the next thing to notice. So notice anytime m is even, y1 of x will terminate. My pen is going crazy today. Terminate. So for example, for 2, what does y1 of x become? It becomes 1 plus negative 2 times 3 over 2 factorial x squared plus, but then the next one will have an m minus 2 in it. So if I plug 2 in there, that becomes 0. And that m minus 2 will be in all the rest of them. So the rest will become 0. So y1 just becomes this, which we can reduce a little bit. Suppose becomes that. So the point is that when m is even, it turns the first power series into just a regular old polynomial, meaning it doesn't go on forever. It just stops like this. So maybe we can do one more. So it's not exactly just looking at the previous one and adding one more, because m changes what this number is too. So you can't just take the previous one and add a new term on. You have to actually go back and plug it in. So that one will stay the same, but then the other ones will not. So this becomes 1 plus negative 4 times 5 over 2 factorial x squared plus, and then the next one is 4 minus 2, and then 4, and then 4 plus 1. That's that 5. But then also we go one more, 4 plus 3 over 4 factorial x to the 4th. So this is the polynomial for m equals 4. This will be 10x squared. This one, we can calculate that high, plus something, x to the 4th. What is that? I guess I'll do it 2 times 4 times 5 times 7 over 4 times 3 times 2, 35 over 3, x to the 4th. So then the point is that we get polynomial solutions to the differential equation when m is even. We get these polynomial solutions, but we also get the power series solution because the other one is not disappearing into a polynomial. It's staying as a big old power series. But this also happens when m is odd. It's just a switch. It just switches. So then what happens when m is odd is y1 of x stays as a power series. But the other guy becomes a polynomial. So let's go ahead and plug in. If I plug in 1, I get y2 of x is x plus, and then the first term is m minus 1, so that becomes a 1 minus 1. So that's just going to disappear. And the rest will all have that too. It goes under here. 3 factorial, sorry. So this is just 0. So the polynomial you get is just x. And so if we look at the pattern for y2, they all have that m minus 1. So they all become 0 from then onward. So that's why it just stops. And you could do y3, which solves the differential equation for m equals 3. So then it would be x plus negative 3 minus 1, 3 plus 2 over 3 factorial x cubed. But then the next one would be 0 because there would be a m minus 3. So the rest would all be 0. So then this polynomial is just x minus, what is this? 2 times 5. It's 10 over 3 factorial x cubed. So I guess that's just 5 over 3. Hopefully I divided correctly. Okay, so yeah, these polynomials are important, but we're going to make them more important in a second. So next what people do is, okay, well, first, okay, so then the takeaway, just to make it extra clear, is that these polynomials solve the DE for corresponding m. So for example, this guy solves for m equals 3, so it specifically, it solves this thing. It was m times m plus 1, aka 12y. But then for some other strange reason, we like to adjust these polynomials slightly. So remember that if you have a solution to a differential equation, that means any multiple constant of it is also a solution. So what we're going to do is we're going to change that C0 and C1. So then C0, y1 of x, also solves it. And so does C1, y2 of x. And what people do now is they choose C0 and C1 to create something called Legendre polynomials. So they pick it according to m. So for m equals 0 and m equals 1, so for m equals 0, you choose C0 equals 1. And for m equals 1, you do the same thing. Choose C1 equals 1. So then what's the polynomial you get? C0 times y1 of x is 1 times 1. Because remember that y1 of x was just 1 for m equals 0. And then this polynomial that you get, this is called the Legendre polynomial for m equals 0. And so what we do is we name it capital P sub 0 of x. So that this is a Legendre polynomial. It's the first one, most boring one. Okay, so what about if m equals 1? Then this is just 1 times x. It's x, and then x, this would be p1 of x. Okay, so then the c's become a little bit more complicated. So for other even numbers, we use this formula. Uh, 1 times 3 times 4, and it's really just to cancel out some fractions. So we'll see that in a second. 2 times 4 times 6. Okay, so then we can calculate P2 of x, because it's just C0 using this formula times that y1 of x. I keep reusing y1 of x, but it's really the y1 of x for this same value, 2. Okay, so what's C0 of x, or sorry, what's C0 here? -1 to the, oh, sorry, m, change the letters, m, these are m's. So it's -1 to the 2/2 times 1. Well, 2 minus 1 is just 1, so it just ends at 1. And then on the bottom is just 2. Okay, and then what was my y1 of x here? It was 1 minus 2 times 3 over 2 factorial x squared. So the point of this is just to flip the negative back and forth. -1 to the 1 is a negative, so I'm going to distribute that negative in. I'm going to keep the 1/2 on the outside. And then the point of this negative is to put the power of x in the front. And so that is P2 of x. So again, what I'm doing is I'm picking C0 based on this formula. And then this polynomial is just what I got way back up here. So you could go back at your notes. And it's right here. y1 of x for m equals 2. Okay, and then I could do P4. It would be C0 times y1 of x, but now the y1 of x for m equals 4. And I'm still using this formula for C0. So that would be -1 to the 4/2 times 1 times 3 over 2 times 4. And then my y1 of x, you can scroll up in your notes and find it, but it would be 1 minus 4 times 5 over 2 factorial x squared plus 2 times 4 times 5 times 7 over 4 factorial x to the 4th. And then now this will be a positive number. And I'll distribute the 3 in, keep the 1/8 on the outside. And now the biggest power of x you see is positive, so I'm going to put that in the first spot and cancel out some of these numbers. This is going to be 35x to the 4th minus 30 x squared minus 3. And again, so this one solves the Legendre polynomial where m equals 4. But this is somehow better because I multiplied it by this number. Okay, let's see. So then for odd m's, 3, 5, 7, we use C1. And now formula is very similar. So you get this even odd, this positive negative flipping. And this sort of weird factorial type thing going on there. So then we can get P3, for example. So it's C1 times Y2 of X, the other power series, whereas this is the Y2 of X for M equals 3. So M equals 3 gives me -1. This becomes 2 over 2. 1 times 3 over 2 times, and then my Y2 of X for that one was X minus, and then it was 2 times 5 over 3 factorial X cubed. And the negative, this becomes a negative, so you distribute the negative. And the 3, to just get a 1/2. And then we'll get a 5x cubed minus a 3x. That's going to be P3. So I'll do one more for you. P5 of X, so that's going to be the one that solves the case for M equals 5. Again, same formula. So C1 is now going to be slightly different. And then again, this is for M equals 5, the polynomial for M equals 5 that we got earlier. So this is -1 to the power of, so 5 minus 1 is 4, times 1 times 3 times 5, over 2 times 4. And now the polynomial that we wrote earlier, x minus 4 times 7 over 3 factorial, x to the third. Once you have the pattern down, it's not so bad. The evens just go and up another one. So this would be, or down 1, and the odds just go up 1. Sorry, up 2 to the next odd number, I should say. And let's see, now this is positive, so that doesn't really do anything. I distribute the top numbers in, and I put the biggest power of X first, and cancel out some stuff, and this will end up with 63 X to the 5th minus 70 X to the 3rd plus 15X. Okay, so once again, just to remind you, this is going to solve 1 minus X squared Y double prime minus 2XY prime plus 5 is M, so 30Y. Okay, so these polynomials, the polynomials that I'm getting using this formula, so I've named them P0, P1, and so on. They are called Legendre polynomials, and they have some very interesting properties. The most interesting one for us that might come into play later if we get to it is that if I do the integral of 2 of them multiplied together, so K and L could just be any 2. So it could be like 3 and 7 or 2 and 6 or 100 and 107. That integral will just turn out to be 0. It's an important property that comes in handy in the future. Okay, but that's it for now. So your goal should be trying to construct some more of these polynomials. I'll try to do like P7 and P8 to see if you got the idea down. Okay, see you next time.